Hi, everyone. So in this talk, I'm going to talk about the work Quantum Soundness of Testing Tensor Codes, which is joint work with Zhengfeng Ji, Thomas Vidick, John Wright, and Henry Yuen. So let's get started by defining what a tensor code is. So I'll start by defining, setting up some notation. So let's just say that C is a linear error correcting code over some alphabet. So we'll write C is a subspace of sigma to the n. So the elements of C are n-dimensional vectors whose coordinates are elements in sigma. And this code has some distance, which we'll denote by the letter D. Okay, so in our applications, we'll think of D as being a pretty big number. And I'll get to that a little bit later. So that's just a basic error correcting code. Now, what's a tensor code? The simplest example of this is what's called the tensor product of C with itself. That's denoted by this C tensor C here. So this is going to be an element, it's going to be a subspace of sigma to the n squared. So the elements of C tensor C will be n squared dimensional vectors whose coordinates are members of this alphabet sigma. So what's the definition of C tensor C? Well, here's how it goes. So say I have some f that's in sigma to the n squared. I'm going to write this as an n by n array, right? Because I have n squared elements in total. And I'll say that f is an element of C tensor C if and only if every row of this array and every column of this array form a code word of C. Could be a different one for each row and for each column. So notice that this makes sense syntactically because every row is an element of sigma to the n. Every column is also an element of sigma to the n. So it makes sense for them to be part of C. And you can verify that this actually defines a linear subspace of sigma to the n squared. So this gives me a linear error correcting code. There's an alternate notation for this that will be very useful for us, which is we can also think of f instead of as an element of sigma to the n squared, we can think of it as a function mapping from n cross n to sigma. So in the picture, that's like the function that maps from the row and column index of a cell to the value in sigma that's written in that cell of the array. And then our condition that every row and column are code words of C is basically saying that if I take the function f and I fix either the row coordinate or the column coordinate to be some value, then the resulting function I get, which is a function of a single variable, that is itself a member of C. That function, I think of it again as an n-dimensional vector over sigma. That should be a member of C. Okay, so that's the basic definition of a tensor code. And you can extend this to allowing for tensor products over more factors. So in general, the object we'll work with is for some base code C, we'll talk about C tensor power m. So this will be a code that lives in the vector space sigma to the n tensor power m. And elements of this code will be representable by n-dimensional arrays. So that's what this f is here. We can alternately think of it as a function from m coordinates ranging over n to sigma. So I can say f is going from n to the m to sigma. And we'll say that f is an element of the code if the restriction of f to every axis parallel line is an element of C. So what that means in the function notation is that if I take f and I fix all the coordinates by but one, the resulting univariate function should be an element of C. So this is really just a generalization of this idea of rows and columns being elements of C. Okay, so that's the general notion of a tensor code. Now, why are these interesting? Well, it turns out that tensor codes are very useful for constructions of objects like locally testable codes and PCPs. And the reason for that is that tensor codes turn out to actually have a sort of natural local test. If I write down a function and I want to check whether it's either a tensor code or far from a tensor code word, I can do this by checking some random locations of f, but relatively few of them. So here's the tester, and I'm going to state it in kind of weird language. I'm going to state it as a two-prover protocol. So if I have two provers, Alice and Bob, and I'm imagining that they interact with some verifier. So here I have Alice and Bob, and I'll stipulate that Alice and Bob are not allowed to communicate during this protocol. So the goal of my tester is going to be this. I want, as a verifier, to convince myself that Alice and Bob share a code word F in C Tensor M, and I want to make sure that they have the same code word in mind. And I want to do this with relatively few queries. So I can't just ask Alice, give me the whole code word, Bob, give me the whole code word, and then I check that they match. So I want to just read a few locations in F and make sure that it's still a valid code word. So here's the test, which I claim to be pretty natural when you look at the definition of the tensor code. The verifier needs to check two things, right? It needs to check that Alice and Bob are consistent with each other, that they have the same code word, and that it actually is a valid tensor code word. So the latter condition is basically saying that this code word restricted to every axis parallel line has to be a member of C. So that's what we'll do basically in the test. We'll have the verifier pick a random point U in the space N tensor M, and a random direction I out of the M possible directions that you could shoot an axis parallel line in. And then we'll define the line, which is basically the line in direction I through U, which is the set of all points that agree with U on everything but the ith coordinate. So now in the test, we'll ask Alice for a function, the value of the function f at point U. We'll get back a value in sigma. And we'll ask Bob for what's supposed to be the value of the function f restricted to the line L. And we'll get back some function that's, I guess, in sigma to the n. And we'll stipulate that this function that Bob returns always has to be a valid code word of the base code. If it's not, we'll just automatically reject here, because if it's a tensor code, then that should be true. So then the final check we'll do is we'll check that Bob's function evaluated at the point U is equal to Alice's value. So it's a consistency check. If that's true, we'll accept. Okay, so that's the test. So it's clear that if Alice and Bob are indeed answering according to a consistent code word F that's an element of C tensor M, then they'll pass in this test with certainty. The statement that's sort of more interesting is the soundness statement, the statement about if you pass with less than certainty, are you close to your code word or not? Turns out to be true that this test is sound, at least if you impose a certain additional condition on the code. So I think many conditions work, and this is much stronger than you need classically, but this will be useful for us. So the condition that we use is something called interpolability. So we'll say that the base code C is interpolable if I give you the values of C on a small number of points, this number t, which is supposed to be the total number of points minus the distance plus 1, then that uniquely determines a valid code word f that agrees with those points. So there are examples of codes that satisfy this condition, most notably codes based on polynomials. So if my codes are, say, degree 2 polynomials over some finite field, then if I give you 3 points, that's enough to uniquely determine a polynomial. And that's indeed the example that we'll use for applications. So if you have this condition, then it was basically shown by Babai, Fortnow, and Lund in the course of showing that MIP is equal to NX, that this test is actually sound. So they showed this for the particular choice of the code being the multilinear code, but if you look at their analysis, it really applies to any interpolable code. So the theorem statement they showed is that if Alice and Bob pass in this two-prover test with pretty high probability, then Alice's answers will actually agree with a code word in the tensor product code with reasonably high probability. So the chance that at a random point, Alice's answer f of u is equal to this code word at point u is 1 minus delta, where delta is some polynomial function of all the parameters you have. So the number of coordinates, this interpolability parameter, the epsilon in your success probability, and 1 over n. Okay, so that's the classical result. So now what do we show? Our result in a nutshell is basically that this test still works even if the two provers, Alice and Bob, share arbitrary amounts of quantum entanglement. So, they're allowed to use this quantum entanglement to do whatever spooky correlations they want. They can measure it in any way they want. There's no restrictions on their computational power. The only restriction is that they can't communicate. And our claim is that this test still works. It's still sound. So more precisely, what does it mean for this test to be sound in the presence of entanglement? Well, the theorem is, suppose Alice and Bob pass the test, actually not quite this test, but a slightly modified one, which we'll see in a second, with probability 1 minus epsilon. Then what we can state is not that there exists a fixed code word that agrees with Alice or with Bob, because that's impossible. What we instead have to state is that there exists a quantum measurement whose outcome is always a valid code word of C to the M, such that Alice's behavior is pretty close to the following behavior. Alice takes her entangled qubits, whatever she has, she measures them with this G measurement to get a code word in C to the M, and then she returns the evaluation of that code word at the given point U. Okay, so classically, you get the same statement where like this measurement G is just the thing that returns a fixed code word, but quantumly you have to allow for randomness and so on. So you have to say that there's this quantum measurement. And of course, there's a quantitative part to this theorem as well. So we said if you succeed with probably 1 minus epsilon, then you're delta close in some appropriate distance metric. And this delta function is kind of similar to the delta from the Beaufort-Nell Lund, but there's one qualitative difference. So there's a 1 over t in the exponent here, which if t is large, then that's pretty bad. But in our applications, I'm thinking of t as being pretty small. And there's sort of alternate techniques that could get you, for large t, you can also get a bound that's better than this 1 over t, but you need a slightly different proof technique. So that's the result. So now let me explain a little bit about why one should care and also what are the technical challenges to proving this. So, okay, first of all, why do we prove this? Who cares about two-prover tests with entanglement? Well, as I said earlier, the classical tensor codes are a key ingredient in PCPs, which are tightly related to multi-prover interactive proofs. It turns out that in the quantum world, these tensor code tests where you have shared entanglement are a crucial ingredient in quantum multi-prover interactive proofs with shared entanglement. So it's this class MIP star, which has been very interesting for quantum complexity theory. And indeed, in our result showing that MIP star is equal to RE, basically this test was one of the key ingredients. So with the base code C being instantiated as I guess actually the Reed-Solomon code, but the code of low degree polynomials over some finite field. So that's one reason to care, is that this sort of abstracts out that analysis from the MIP star equals RE result and presents it in a standalone way. Another reason to care is that if you're just interested in quantum information, the tensor code test can actually be viewed as sort of a very like a natural sort of generalization of the magic square game of Mermin and Perez. So this is sort of famous as an example of the weirdness you can get with quantum entanglement. So the contrast between that and the tensor code test is I think, interesting. So let me say a few words about that. So what's the magic square? Let me present it in a language that's a little bit like a tensor code. And if you bear with me for a second, it looks like my iPad has ceased to sync with the screen share. Better. So, okay, what's the magic square? The magic square is a 3x3 grid. You're supposed to fill it in with bits such that all the rows sum to 0 and all the columns sum to 1. Okay, you can think of this as kind of like a tensor code where the code, the two codes that you're taking the tensor product of are the code of all 3-bit strings whose parity is 0, and the code of all 3-bit strings whose parity is 1. This is not quite a linear code, so it's a little bit outside of the definition, but bear with me for a second. So this code, C1 tensor C2, turns out to be empty. There's no code words in this code. And you can see that by just looking at the constraints. So if I sum all the rows in this array, I have to get 0, right? Because each one sums to 0. If I sum all the columns, I have to get 1 on 2, because that's the constraint. But this is the same sum expressed in 2 different ways. So there's a contradiction. Therefore, it's impossible to fill out an array to satisfy all these constraints. So there's no code word. There's nothing in this tensor code. Yet, it turns out that if Alice and Bob share quantum entanglement, then they can pass the tensor code test with certainty for this set of constraints. So there's a strategy that uses quantum entanglement that succeeds with certainty in the tensor code test, even though there's no valid code word that exists at all. And sort of the reason that this happens is that in quantum mechanics, you can have measurements that are not simultaneously measurable. You could measure one or the other, but not both. This is like the Heisenberg uncertainty principle. And the clever strategy that Alice and Bob have to use is it's a strategy where there's a measurement for every cell in the square, and measurements that aren't on the same axis parallel line, so the same row or column, these measurements don't commute. So you can't simultaneously measure them. But on the same axis parallel line, they do commute, and so you'll never detect a problem in the tensor code test. So this seems pretty spooky. So it even seems to suggest that it's kind of hopeless for the tensor code test to work against entanglement, because we could use something like this. So that's the main challenge in our analysis, to show that this doesn't happen in general. So the way we do that is sort of, we do 2 things. The first thing we do is we cheat a little bit. So we modify the test to actually introduce a new test that forces the measurements for every pair of cells in this array to commute pairwise, at least on average. So the way we do that is we just do a similar line versus point test, but instead of just doing axis parallel lines, we also do diagonal lines. Okay, so that those join to every pair of points. Well, that turns out to not be enough. Indeed, it may not even be strictly necessary. Turns out the real thing that helps us out in our analysis is actually the error correcting properties of the tensor code itself. So in our analysis, what we're trying to do is something like construct a single measurement that simultaneously gives you a value for every cell in the array. And the way our proof goes is by induction. It sort of does this for every affine subspace of lower dimension, and then it pastes things together. And now you might worry that if you have this for, say, 3 parallel affine subspaces, there's no reason for these measurements to be simultaneously measurable. But turns out that by looking at the fact that you're a tensor code, so you have to agree with this restriction of the global code word to a vertical axis parallel line, and this restriction is itself a code word of the base code C with high distance. Like, these properties let you argue that these measurements are pretty close to commuting, and therefore you can measure them simultaneously. So the error correcting properties of the code are what save us from something like magic square happening. So that's all I have time to say about the analysis. I'll just conclude by saying a few words about context and future work. So this paper builds on a template introduced by Ito and Vidick when they were showing that MIP star contains NX. And they gave an analysis for a version of this test, except it had 3 provers and it was specialized to multilinear functions. It also replaces an incorrect analysis of the plane versus point low degree tests that appeared in Vidick 13 and paper by myself and Vidick in 18, for which a bug was discovered last year or 2 years ago. So it replaces that test in most contexts. And also, it is sound even against a slightly larger class of strategies, these so-called infinite dimensional synchronous strategies. So that uses some new mathematical tools due to this work by De La Salle from 2021. So there's several interesting open questions that I'll close with. Are the subtests really necessary, like this diagonal lines test? And can we improve the error dependence to match what you get classically, and other interesting applications to interactive proofs or other areas? So that I'll stop. Thank you for listening, and I hope you enjoy the live talk at the conference.